So this video is on section 5.2, something called the characteristic equation. This is the section where we're going to learn how to find the eigenvalues and eigenvectors. And so let's just remind you here. If you have a matrix A, then whenever you satisfy the equation, A times a vector is equal to lambda times a vector, whenever that is true, that is going to be an eigenvalue and eigenvector, where the number lambda is the eigenvalue and the vector x is the eigenvector. Now there was something I didn't mention before, and the only thing is that your x vector has to be not the 0 vector. Otherwise it's not really in the same direction because they're just 0 everywhere. It doesn't really help anything. Okay, now how are we going to actually solve for these things? Well, if I take this equation here and I move things to the left side, ax minus lambda x equal to 0. And what I'm going to do is I'm going to kind of factor out the x here, but to be careful, because if I were to write down this, kind of factoring out the x in the most obvious way, this would not make any sense, because this right here is a matrix and this is a number. So you cannot subtract them. So it doesn't work to do it that way. But we can do it slightly differently here by realizing that if I put the identity matrix here, it doesn't change anything, because the identity matrix is still doesn't change any other matrix when you multiply it by it. So then now I can factor this out, and I'd have a minus lambda I times x equal to 0. Okay. Well, what I have now is I have a system of equations over here. This is your coefficient matrix, and it equals to 0. Now, we saw before that certainly if x is 0, this is a true statement, but we want, again, a non-zero number, a non-zero vector x to solve this equation. And if you remember the invertible matrix theorem, which you may or may not remember at this point in time, if I want a non-zero solution to this equation, then the only way that can happen is if this matrix here, if that is a singular matrix, or in other words, the determinant is 0. And this right here is what's called the characteristic equation. And this right here is exactly how you're going to find eigenvalues for a problem. So let's look at the matrix 1, 2, 2, 1. And I'm going to ask you to find the eigenvalues. So you always just write down what a minus lambda I is. Well, a is 1, 2, 2, 1 minus lambda times the identity 0, 1, 0, 0, 1. And if you just work this out, you're going to get 1 minus lambda, 2, 2, and then 1 minus lambda. And then we need the determinant of this thing. And 2 by 2 determinants aren't that bad, you know, cross multiply and subtract. 1 minus lambda times 1 minus lambda minus 2 times 2. You're going to have lambda squared minus 2 lambda plus 1 minus 4 is lambda squared minus 2 lambda minus 3. But remember, we want this result to be equal to 0. And we can go ahead and factor this. And lo and behold, that gives us the 2 eigenvalues from when we look at this matrix last video. And so whenever you're doing this, whenever you're trying to find eigenvalues, this is going to be the exact process. You do a minus lambda I, you take the determinant, set it equal to 0, and you solve it. And since we're going to have only 2 by 2 matrices in this class, then that means you are only going to have quadratic equations here, and so you just have to factor your quadratic equation or quadratic formula possibly, and that would give you your 2 eigenvalues. So it's very straightforward here how we're going to do this. That's all we got to worry about. The finding eigenvectors is going to be a little bit more involved, unfortunately. And so let's go ahead and look at that now. So write down what we had. A is 1, 2, 2, 1. And we already learned that the eigenvalues were 3 and -1 by solving the characteristic equation. So then the next thing we need to do is we need to find the eigenvectors. Now, really quickly, remember before that whenever you have an equation, if it has more than one solution, then it has infinitely many. And that's the situation that we're going to be in here. So what that means is there are going to be infinitely many solutions to this problem. There's going to be infinitely many eigenvectors you could tell me. And that corresponds to having a free variable. So you are always will have a free variable. Just keep that in mind. So if you're solving these problems and you don't get a free variable, then you did something wrong here. It's not going to be the eigenvector. Okay, so when you want to find an eigenvector, you pick whatever eigenvalue you want. So in this case, I'm going to pick the eigenvalue 3. And remember, there are going to be different eigenvectors for different eigenvalues. So I picked this eigenvalue here. And now I'm going to go ahead and look at the equation. A minus lambda I x equal to 0. And what is A minus lambda I here? A is 1, 2, 2, 1 minus 3 times the identity. Do a little bit of work here. I'm going to get minus 2, 2, 2, minus 2. And so then I want to go ahead and say, okay, well, that's my matrix A minus lambda I. So then I will go ahead and set up the system of equations here using my augmented matrix, -2, 2, 2, -2, 0, 0. So that right there gives you the augmented matrix form. You go ahead and put it into reduced row echelon here. And put that in your calculator, and you should get 1, -1, 0, 0, 0, 0. And you see how we have our one pivot here, which leaves me my one free variable. And so that means that I have, if I were to write out the equation here, it would be the equation x minus y is 0. So that means x equal to y. And that means if I have the solution of this system equation, xy, it's yy, because x equal to y, and that's y times 1, 1 here. And that means my eigenvector for lambda is 3 is the vector 1, 1, which again is what we saw in the previous video, but now you see how we can solve for it instead of just knowing what it is. Okay, now I solved it in general. I had my free variable here. But the thing is if you don't like that, all you have to do is just pick x or y to be whatever number you want to, solve for the other one, and you're going to get an eigenvector. So if you had, say, gotten 2 here, you would have had 2, 2, and that would be a perfectly valid solution. Or you could have 17, 17. All of these would be perfectly valid eigenvectors, but all I'm going to ask you for is to give me one of them. Just need to have one eigenvector. Now let me do the same thing here with lambda is -1. So there is lambda is -1. And we're going to go ahead and do my A minus lambda I here. So you got to be careful that it is subtract lambda I, and if lambda is a negative, it's going to become plus here. So we're going to have the following matrix, 2, 2, 2, 2. And then we set up our system of equations where we throw on 0 on the right-hand side. Again, the reason why we do this is because we want this to be equal to the 0 vector. And we do our reduced row echelon form, and we're going to get this. Once again, we have one pivot and one free variable. And if we write out the equation, it's x plus y is 0. So x is negative y. So my solution xy is negative y, which is y times negative 1, 1. And so that means for lambda is negative 1, my eigenvector is the vector negative 1, 1. Now I do want to kind of point out that that is not the same as we had in the last video, but if I chose instead y to be negative 1, I would have gotten the vector I had last time, which is 1, negative 1. So again, this vector here is perfectly fine, as well as any multiples of it. Those would all be perfectly valid eigenvectors as well. And again, all I'm going to do is ask you for one of them. So the general process is you want to take your determinant of a minus lambda I, set it equal to 0. That will give you your eigenvalues lambda, both of them. Then for each one of them, you go to this process to find a single eigenvector, and then you'll be good. Then you'll have the answer for what we're looking for. Okay, so we'll stop here and we'll do another example on the next video.